Today we explore one of nature's most mysterious phenomena, how pure water droplets can create electricity and light from nothing. When we spray neutral water into tiny droplets, they spontaneously generate electric charges and produce actual lightning at microscopic scales. Let's start with the fundamental puzzle that stumped scientists for years. Water molecules have no net electric charge. They're electrically neutral, with equal positive and negative charges. Here's a water molecule. One oxygen atom bonded to two hydrogen atoms with no net charge. So here's the question. If water is neutral, how can pure water droplets spontaneously develop electric charges? The answer lies in surface chemistry. When we create tiny droplets, the surface breaks the normal symmetry of water. The key to understanding microlightning is what happens at droplet surfaces. In a water droplet, molecules at the surface experience different forces than molecules in the bulk interior. Research shows that hydroxide ions, which are negatively charged, preferentially accumulate at water surfaces. Water naturally dissociates into hydrogen ions and hydroxide ions in a dynamic equilibrium. At the surface, we get more hydroxide than hydrogen ions, creating a negative surface charge. Now let's see exactly how charge separation occurs when we spray water. When we break bulk water into droplets, the hydroxide-rich surface becomes the outer shell, while excess hydrogen ions remain in some droplets. Most droplets acquire a net negative charge because their large surface area is enriched in hydroxide ions. The charge Q equals negative N times the elementary charge, where N is the excess number of electrons. Let's calculate actual numbers to understand the magnitude of this effect. Let's consider a typical microdroplet with diameter of 10 micromolars. That's 1/100th of a millimeter. That's 10 times 10 to the negative 6 meters, or 10 micrometers. The surface area is 4 pi r squared, which gives us about 3.14 times 10 to the negative 10 square meters. Experiments show typical surface charge densities around 1 excess electron per square nanometer of surface. That's a surface charge density of about 0.16 coulombs per square meter. Multiplying surface charge density by area gives us about 50,000 excess electrons per droplet. That works out to about 8 femtocoulombs of charge per tiny droplet. Femto means 10 to the negative 15. This charge creates enormous electric fields inside the tiny droplets. The surface charge creates electric field lines pointing radially outward from the center of each droplet. How strong is this electric field inside our 10 micrometer droplet? The electric field at the droplet surface is given by Q over 4 pi epsilon 0 r squared. For our droplet, this gives an electric field of about 10 million volts per meter. This is comparable to the electric fields and lightning bolts during thunderstorms. That's why we call it microlightning. The real magic happens when charged droplets collide or come very close together. When two negatively charged droplets approach each other, their electric fields add up. The total electric field between them can reach 20 million volts per meter or more. At these extreme field strengths, even air molecules break down and ionize, allowing current to flow. This creates a tiny electrical discharge, a microscopic lightning bolt bridging the gap between droplets. These electrical discharges produce visible light, creating the luminescence we can observe. In the strong electric field, free electrons accelerate to very high velocities. They gain kinetic energy equal to the charge times the voltage difference they traverse. These energetic electrons then collide with nitrogen and oxygen molecules in the air. When electrons hit molecules, they excite them to higher energy states. When these molecules relax, they emit photons of light. The energy of emitted photons equals Planck's constant times the frequency. The emitted light spans the visible spectrum from about 400 to 700 nanometers, which is why we can see these tiny flashes. The most surprising discovery is that microlightning can drive chemical reactions. The highly energetic electrons in these discharges carry enough energy to break chemical bonds in molecules. For example, electrons can split water molecules into hydrogen and hydroxyl radicals. These radicals are extremely reactive chemical species with unpaired electrons that want to form new bonds. A radical is like a chemical species with open arms. desperately seeking to bond with other molecules. This leads to one of the most profound implications: creating organic molecules without life. In the presence of simple molecules like water, carbon dioxide, and nitrogen, radicals can build complex organic molecules. Carbon dioxide plus water, driven by electron impacts, can produce organic compounds. Experiments have detected formaldehyde, formic acid, and even precursors to amino acids forming in microdroplet sprays. Here's a simple organic molecule that can form through these processes, with carbon, hydrogen, and oxygen atoms linked together. This raises a fascinating question. Could microlightning in natural water sprays have helped create organic molecules on early Earth? The answer is possibly yes. Anywhere we have water breaking into fine sprays, like ocean waves, waterfalls, or rain, this process could occur. This phenomenon might have played a role in the origin of life on Earth. On early Earth, before life existed, there were countless sources of water spray, primitive oceans, volcanic steam, and meteorite impacts. Creating the building blocks of life requires energy sources to drive chemical reactions uphill. Traditional theories focused on UV light from the sun, atmospheric lightning, and heat from volcanoes. Microlightning adds a new, ubiquitous energy source that operates wherever water forms fine sprays. Estimates suggest microlightning could deliver about 1 watt per square meter of energy to drive chemistry. Modern experiments have confirmed this remarkable phenomenon. Researchers use high-speed cameras capable of capturing millions of frames per second, combined with spectrometers to analyze light. The experimental setup sprays pure water through a nozzle, while detectors capture the resulting flashes of light. Results show brief flashes of light lasting only nanoseconds, consistent with electrical discharges. The flash duration is typically 1 to 100 nanoseconds, billionths of a second. Chemical analysis of the spray products confirms the production of simple organic molecules. Let's calculate the total energy involved in these phenomena. Consider the energy released in a single microlightning discharge between 2 droplets. The energy stored in the capacitance of a droplet is 1/2 CV squared. For our 10 micrometer droplet, the capacitance is about 5 times 10 to the negative 16 farads. The voltage is approximately 1000 volts based on our earlier field calculations. This gives an energy of about 2.5 times 10 to the negative 10 joules per discharge event. This tiny amount of energy is actually enough to break about 1 trillion chemical bonds, making chemistry possible. How does microlightning compare to the regular lightning we see in storms? Here's a comparison of scale. Regular lightning releases billions of times more energy than microlightning. A typical lightning bolt releases about 1 billion joule of energy. A single microlightning event releases only 10 to the negative 10 joules. However, microlightning events happen trillions of times more frequently in sprays, potentially matching total energy output. Let's dive deeper into why charges accumulate at water surfaces. The surface of water has a unique electronic structure where molecules are partially oriented. At the surface, water molecules orient with oxygen pointing outward, creating a dipole layer. This creates a surface potential difference of about 0.1 to 0.5 volts. Hydroxide ions require less energy to exist at the surface than in bulk water, explaining their preference for surfaces. The free energy change for surface hydroxide is less than for bulk, driving them to the surface. This discovery opens exciting possibilities for applications and future research. One application is water disinfection. Microlightning produces reactive species that can kill bacteria without adding chemicals. It offers new green chemistry methods for synthesizing organic compounds using only water and electricity. A simple spray apparatus could become a reactor for synthesizing valuable compounds from simple starting materials. This also has implications for atmospheric chemistry, as clouds and rain produce countless microdroplets. On other planets and moons with liquid water, microlightning could drive chemistry even in the absence of life. From a thermodynamics viewpoint, microlightning converts mechanical energy into chemical energy. When we spray water, we do mechanical work to break it into tiny droplets, increasing surface area. The work done equals the surface tension gamma times the change in surface area. For water, Surface tension is about 0.072 newtons per meter. This mechanical work becomes stored as electrical potential energy in the charged droplet surfaces, which equals 1/2 q squared over c, the electrical potential energy. Finally, during discharge, this electrical energy converts into chemical bond energy in newly formed molecules. At the smallest scales, quantum mechanical effects become important. When droplets are extremely close, electrons can quantum tunnel through thin water layers. The tunneling probability decreases exponentially with barrier thickness d. Protons can also tunnel between molecules, facilitating rapid charge transfer in these systems. This diagram shows a particle tunneling through a potential barrier, a quantum effect crucial in these nanoscale phenomena. We can identify microlightning events by their unique light spectra. Each excited molecule emits light at characteristic wavelengths, creating a unique spectroscopic fingerprint. A typical emission spectrum shows peaks at specific wavelengths, identifying which molecules are excited during discharge. The wavelength equals Planck's constant times the speed of light divided by the photon energy. Common spectral peaks include hydroxyl radical at 309 nanometers and excited nitrogen at 337 nanometers. Dissolved gases in water significantly affect microlightning behavior. Normal water saturated with air contains dissolved oxygen and nitrogen gases. Typical concentrations are 250 micromolar oxygen and 500 micromolar nitrogen. During microlightning discharge, these dissolved gases become ionized, participating in the chemistry. For example, nitrogen molecules can be split into reactive nitrogen atoms by electron impact. This provides a mechanism for nitrogen fixation directly in water droplets, potentially important for prebiotic chemistry. The effectiveness of microlightning depends critically on droplet size. Here are droplets at 3 different scales: 1 micrometer, 10 micrometers, and 100 micrometers in diameter. The optimal size range for observing microlightning is from 1 to 50 micrometers. In conclusion, microlightning in water sprays can generate significant amounts of charge and produce light, with potential applications in chemistry and our understanding of the origins of life on Earth.